application or of measuring cell potentials is the determination of solubility products of slightly soluble salts. So an example will be lead sulfate, which has this equilibrium with its ions. So the first step is to look at your standard reduction potential table and determine which half cells would lead to this reaction. So we take the lead sulfate half cell and the lead 2 plus half cell. So for this one, our half cell reaction is the reduction of lead sulfate, which gives solid lead plus sulfate ion, and this has a standard reduction potential of negative 0.3546 volts. For the other half cell, we have the half reaction lead 2 plus 2 electrons forming solid lead. And this one has a standard reduction potential of negative 0.1265 volt. So if we take the reverse of this reaction, and then, so what we do with the reduction potential is to take the negative of the reduction potential. If we add the two equations, we get lead sulfate plus 2 electrons plus solid lead forming solid lead plus sulfate plus 2 electrons. So we cancel the electrons in the solid lead. So we forgot about the lead 2 here. So we end up with our desired equation. And this cell has a potential of negative 0.2281 volts. The cell potential is related to the solubility product constant by this equation. So we plug in the cell potential. R is the gas constant in joule per mole Kelvin. The temperature is 298.15 Kelvin because the table that I used are reduction potentials taken at 25 degrees Celsius. N here is 2, N is the number of electrons involved in the reaction. And we have Faraday's constant, which is 96,485 coulombs per equivalent, times L and Ks. So if we evaluate for the solubility product constant, we get a value of 1.942 times 10 raised to negative 8. Wondering what how the previously described cell looks like. So here is a diagram showing the cell. So we have two electrodes. One is just lead metal and the other is lead metal coated with solid lead sulfate. Both of these electrodes are dipped in the lead sulfate solution.